Hi there, my name is Abdul Rehman, and this presentation outlines the research I am undertaking for my MSc dissertation. My project is titled Machine Condition Monitoring for Defect Detection in Fuse Deposition Modeling, and it explores the application of AI-based solutions to improve the reliability and quality of additive manufacturing processes. This presentation covers my research background, methodology, and proposed future execution strategy. So, next up, we have research background, aims, and objectives. So, fused deposition modeling or FDM is one of the most popular 3D printing techniques. However, it's vulnerable to mechanical and thermal issues like nozzle clogging, under extrusion, and warping, all of which can ruin a print, waste material, and delay production. The aim of my research is to explore how real-time machine condition monitoring can help solve this using smart, AI-driven systems to detect problems early and enable better quality control. To achieve this, I've set forth four objectives. Number one, investigate the causes and types of common FDM defects. Secondly, review existing AI-based monitoring systems. Thirdly, identify gaps in current solutions. And fourthly, and propose a technically realistic framework for intelligent monitoring. So next up, we have problem statement and research significance. So one major challenge in FDM is that many defects aren't detected until after the print is complete, at which point the damage is already done, right? So most existing systems either respond too slowly or lack flexibility to work across different machines, filaments, or setups. This research is significant because it targets that exact issue by developing a smarter, faster, and more adaptable monitoring system. If successful, this solution could save time and material and improve quality and contribute towards more sustainable and automated manufacturing practices. Next up, we have literature survey research methodology. So, to build a strong foundation, I conducted a systematic literature survey. I used platforms like Google Scholar, Science Direct, MDPI, etc., with keywords such as FDM defect detection, YOLO additive manufacturing, and sensor based FDM monitoring. Only peer reviewed papers published between 2020 and 2024 were included, especially those with measurable performance metrics like accuracy or latency, etc. I selected 15 high quality papers, including extensive case studies as well, grouped into three themes: vision based methods, sensor based systems, and hybrid approaches combining both. These categories structure the basis of my full literature review. Next up, we have literature review, key insights, and themes. So, across the reviewed papers, five key significant insights emerged. First, common defects like nozzle clogging, over or under extrusion, and warping were the primary targets. Vision-based systems using deep learning models like YOLO V3 Tiny and YOLO V8 performed very well in surface level defect detection with real-time performance and high accuracy. Sensor-based systems using models like temporal convolutional networks or LSTMs were more effective at detecting internal issues like thermal fluctuations or vibrations. Hybrid models combining camera and sensor data showed the most promise. However, big gaps remain. Most systems struggle with generalization, lack corrective feedback, and often require expensive hardware. These limitations are exactly what my proposed research aims to address. Next up, we have the planning stage, Gantt chart, risks, and resources. So the research was planned using a structured Gantt chart. It began in January this year with topic selection and literature survey, followed by deep review and report writing in February and March. I also performed a risk assessment. For instance, data access was a concern, so I've ensured that open source datasets are available. Technical complexity will be addressed by keeping the first stage simulation based. And since supervisor availability may be limited, I'm using asynchronous updates to stay on track. So in terms of resources, I'll be using Python machine learning libraries, Google Colab for model testing, and potentially Jetson Nano, possibly future for future embedded development, but not confirmed. So next up we have legal, social, ethical, and professional issues, LSEPI. So I've carefully considered all legal, social, ethical, and professional responsibilities. Legally, there's no human data involved, and all datasets and tools are open access and properly cited. Technically, there's no misrepresentation. Model limitations will be clearly stated. Socially, this research promotes responsible automation. It is not about replacing jobs but improving print quality and reducing wastage. Professionally, I followed ethical course from BCS and IEEE, maintained full academic integrity, and incorporated feedback wherever possible. Next up, we have proposed methodology about the future research plan. So, looking ahead, the proposed methodology includes collecting visual and sensory data, either from real world setups or existing open datasets, and applying deep learning models. For image data, I'll use YOLO V8 or CNNs. For time series data like vibration or temperature, I'll test TCNs or LSTMs. If feasible, I'll also explore fusion models that combine both input types. So, evaluation will use accuracy, latency, and generalizability metrics. Real-time performance is a key goal, and if hardware allows, I'll test deployment on an embedded device like Jetson Nano. Otherwise, I'll keep it as simulation-based only. So, lastly, we have conclusion and impact of this research study. So, in summary, this project addresses a real and impactful problem in 3D printing, that of undetected defects ruining parts and wasting material and time alike. Through literature review, I've shown that AI driven monitoring is the best path forward. However, current systems still fall short from the expectations and industry requirements. My proposed research will aim to fill those gaps with a lightweight, scalable, and real time system built on vision and sensory data. And since I'm a January 2025 intake student, I have until August of 2026 to complete this work, giving me enough time to carry out testing, validation, and implementation at a very high level because it gives me with an advantage of having a 1 year in advance. So that was pretty much it as far as my presentation is concerned. And thank you so much for your time.